Effects of 21 days of intensified training on markers of overtraining. Montana Center for Work, Physiology, and Exercise Metabolism, University of Montana, Missoula, Montana. Introduction. In an effort to enhance performance, athletes increase their training volume and intensity at strategic times during their competitive season. During these periods of intensified training, an increase in training volume, training intensity, or both, athletes may be at risk for developing overtraining syndrome. Overtraining has been defined as an accumulation of training and or non-training stress resulting in long-term decrement in performance capacity with or without related physiological and psychological signs and symptoms of overtraining, in which restoration of performance capacity may take from several weeks to months. By comparison, overreaching results in short-term decrement of performance taking only several days to weeks to recover. More recently, further clarification, detail, and consistency has been made in these definitions with the publication of a consensus statement. Briefly, overtraining is used as a verb to describe the process of intensified training with many possible outcomes. These outcomes may be a functional overreaching, in which supercompensation may occur after an acute decline in performance consistency with the normal training response. Non-functional overreaching, in which performance may decline or fail to increase but will recover after a period of several weeks or months, and overtraining syndrome, in which the decrease in performance may take months to recover. Importantly, the diagnosis of overtraining syndrome requires exclusion of other pathological etiology. These definitions suggest that performance is the criterion measure for overtraining syndrome and or overreaching, despite many other proposed physiological and psychological measures. However, the mechanisms, criteria, and symptoms for overtraining are poorly understood, despite the importance of identifying early indicators that may lead to the performance decrements seen with overtraining and overreaching. Past literature suggests a wide range of physiological markers that may serve as early identifiers or potential markers of overtraining, a common practice for athletes is to measure morning resting heart rate, HR. Popular press suggests that a 10% increase in resting HR may be indicative of overtraining. However, investigations on resting HR as a marker of overtraining are not in agreement. Although some papers have reported increased resting HR as a sign of overtraining, others have not. Submaximal exercise HRs have also been reported to increase during a state of overtraining. Other common markers that have received debate in the literature include measures of immunosuppression and mood disturbance. Because immunosuppression has been associated with long duration, high intensity exercise, markers of immune system function such as secretory IgA may be useful in diagnosis. McKinnon has reported lower salivary IgA concentrations in athletes who showed signs of overtraining when compared to athletes who were overtrained but did not show signs of overtraining. Overtraining paradigms have demonstrated negative mood disturbances in athletes, despite physically active individuals having more positive mental health than persons who are less physically active. Deterioration of mood state often precedes a drop in performance, indicating that this approach may be useful in the early detection of overtraining. The Profile of Mood States questionnaire, POMS, POMS, has been shown to detect differences between the non-functional overreached individual and a control subject. Additionally, blood-borne markers have been associated with training stress and overtraining. The testosterone cortisol ratio has been used as a measure of anabolic and catabolic balance, with a decrease of 30% being suggestive of overtraining. However, others have argued that overtraining cannot be monitored using this ratio during high-intensity exercise, and is better used to monitor exercise stress and recovery. Inconsistency in many of these proposed markers suggests the complexity of overtraining and the different states and severities of overtraining. It is difficult to discern in these studies which subject samples were overreached, overtrained, or simply trained. Although previous literature has focused on the identification of markers of overtraining, the purpose of the present investigation was to impose a period of quantifiable intensity training to determine if commonly used diagnostic markers of overtraining parallel changes in physical performance and thus overreaching and overtraining status. Furthermore, we aimed to differentiate individuals with and without symptoms of overtraining using physiological and psychological symptoms that have been previously reported. Methods. Experimental approach to the problem. The period of intensified training was organized in a 21-day bicycle tour through the mountains of western USA. Participants cycled at a self-selected work rate for the bulk of the training time, except for scheduled performance trials. Training consisted of cycling approximately 169 plus or minus 4 kilometers a day on each of the 21 days except for 10 and 20 rest days, for a total of 3,211 kilometers. This represented a 418 plus or minus 142% increase in training time compared to the 60 days before the study. Participants completed the training on identical, size-adjusted racing bicycles, Orbea, USA, North Little Rock, Arkansas, USA, equipped with a power tap power meter integrated into the rear wheel. Ceres Cycling, Madison, Wisconsin, USA. Ad libitum, energy was provided in the form of a hot breakfast and dinner from a catering service that specialized in bicycling tourists. During the time spent cycling, participants were provided with as much commercially available supplemental foods as desired, energy bars and sports drinks. Gatorade, Chicago, Illinois, USA. Subjects slept in tents at prearranged sites during the day. Subjects. 10 male participants were recruited from the local triathlon and cycling community. The data from the 2 individuals are not included in the current data set because of technical issues with equipment. Therefore, the data represented in this paper are for the 8 participants. Descriptive data are presented in Table 1. Participants completed the protocols in August, which is nearing the end of the road cycling and triathlon season in the Northwest USA. According to the criteria for classification of a world-class cyclist put forth by Junkendrup et al., these subjects would be classified as trained to well-trained cyclists. Subjects were informed of the experimental procedures and signed informed consent statements. All procedures were approved by the University of Montana Institutional Review Board for any data collection. Procedures. Performance trials on days 1, 4, 7, 11, 14, 17, and 21. A 1-hour performance time trial was conducted on open roads. On these days, participants rode 5 through 10 kilometers as a warm-up before starting the performance trial. Time trials were started at 2-minute intervals, and riders were instructed to ride as hard as possible during the 1-hour period. Power output may be dependent upon terrain that the performance trial occurs, but less so than speed and hence distance. Therefore, average watts produced during this 1-hour time trial were recorded as performance capacity. Altitude may also influence cycling capacity. Therefore, days 1 and 21, which were conducted on the identical course, were analyzed independently. Of the other trials, in the effort to eliminate the impact of variable terrain and altitude, distance and speed were not used as the performance measure because the terrain varied by day, except for days 1 and 21, which were on an identical course. Profile of mood states. The profile mood states brief quick scores performs MHS North Tonawanda, New York, USA, were used to track mood state during the intensified training period. These forms allow for measurement of total mood disturbance, tension, depression, anger, vigor, fatigue, and confusion. This 30-question form was administered to participants in the morning before any activity on days 1, 4, 7, 11, 14, 17, and 21. This version of PALMS is comparable with that of the original PALMS. Heart rate. Morning resting HR submaximal stepping HR and HR after 30 seconds of seated recovery were measured on days 1, 4, 7, 11, 14, 17, and 21 before any other activity. Resting HR was measured immediately upon waking for 5 minutes in a seated position. Participants then stepped up and down on a 20.32 centimeter step to a metronome, 88 beats per minute, yielding a cadence of 22 steps per minute for 1 minute. Participants then immediately sat down and recovery HR was recorded for 30 seconds post-exercise. The post-exercise recovery HR was then converted to percent recovery of resting HR. Saliva collection. Saliva samples were collected by the passive drool technique on the morning and immediately after cycle training days 1, 4, 7, 11, 14, 17, and 21. Salivary flow rate was calculated by recording the time each individual took to fill a collection vial to 3 milliliters. The samples were weighed to verify the volume and then immediately froze on dry ice until they were transferred to a negative 80 Celsius freezer and stored for later analysis of testosterone, cortisol, secretory IgA. Testosterone, cortisol, and secretory IgA, salivary testosterone, cortisol, and secretory IgA were measured in duplicate in the saliva samples using a competitive immunoassay on the plate reader, model 680XR, Biorad, Hercules, California, USA, at 450 nanometers. In accordance with the manufacturer's protocols, Salometrics, State College, Pennsylvania, USA, absolute secretory IgA was then corrected for salivary flow rate. If the coefficient of variation for duplicate samples was greater than 10%, then samples were reanalyzed. The values reported in this manuscript are similar to others. Salivary measures of IgA, cortisol, and testosterone were measured due to the non-invasive collection method. The salivary markers changed similarly in response to stimuli as serum measures and may be more responsive to exercise. Maximal exercise capacity. Maximum oxygen consumption, VO2 max, and workload associated with VO2 max were measured for each subject before and after intensified training using a graded exercise protocol. Briefly, the protocol started at 95 watts with an increase of 35 watts every 3 minutes on an electronically braked cycle trainer ergometer. CompuTrainer Racemate Incorporated, Seattle, Washington, USA. Participants rode to volitional fatigue. Maximum workload was calculated to the highest completed stage in watts plus the proportion of time in the next stage multiplied by the 35 watt stage increment. Expired gases were collected during the test using a calibrated metabolic cart. Parvomedics Incorporated, Salt Lake City, Utah, USA, and recorded at 15-second intervals. Individual response. To determine the response of each individual participants were classified by 4 markers of overtraining: above 5% reduction in time trial performance, increase in resting HR above 10%, increased submaximal exercise HR by more than day-to-day variation of 8 beats per minute, and above 30 degrees decrease in testosterone cortisol ratio. These 4 markers were selected based on the availability to determine an individual critical value for each marker that, if reached, may imply a symptom of overtraining. In that individual, as described in previous literature, individuals with 2 or fewer symptoms throughout the training period were classified as asymptomatic, whereas individuals above 2 symptoms were classified as symptomatic. Characteristics of these groups were then compared to determine if these groups differed. Statistical analysis. Differences in performance and overtraining parameters over 21 training days were compared using one-way repeated measures analysis of variance, ANOVAs. Additionally, a paired t-test was used to further analyze performance on day 1 versus day 21 when testing conditions were controlled for terrain, altitude. Salivary, testosterone, cortisol, and testosterone-cortisol ratio were compared over training days and by time of day, pre versus post acute exercise, using two-way repeated measures, ANOVAs. In the event of significant F ratio, the false detection rate method was applied to locate differences and correct for multiple comparisons. All ANOVAs were performed using SPSS for Windows version 9, Chicago, Illinois, USA. A probability of type 1 error less than 5% was considered significant. P is less than or equal to 0.05. All data are reported as means plus or minus SE. Results. Training. During 21 days of intensified training, the participants cycled 3,211 kilometers, 169 plus or minus 4 kilometers a day, plus 2 rest days, over varied terrain. See Figure 1. For the route profile, the time spent riding represented a 418 plus or minus 142% increase in training time per day compared to the 60 days before this investigation. The riders averaged 167 plus or minus 4 watts, 47 plus or minus 1% of pre-training max in watts during the training. See Figure 2 for a detailed breakdown of riding intensity. Performance. Average power output in watts during the 1 hour time trials was no different. P is greater than 0.05 on day 4 plus 2 plus or minus 2%. Day 7 plus 2 plus or minus 2%. Day 11 minus 6 plus or minus 3%. Day 14 plus 5 plus or minus 3%. Day 17 plus 3 plus or minus 2%. Or day 21 plus 4 plus or minus 4% than it was on day 1, Figure 3. Furthermore, a separate analysis of day 1 versus day 21, in which 1 hour performance trials were conducted on the identical course, revealed no statistical difference. P is greater than 0.05 as a result of the intensified training. Heart rate. There was no change at any time point in resting HR 49 plus or minus 1. Step test exercise HR 92 plus or minus 1. Or percent HR recovery 30 seconds post exercise 64 plus or minus 1% from day 1 values. Figure 4. Salivary markers. There was no change in salivary secretory IgA in absolute terms or relative to salivary flow rate. Figure 5. And from day 1, salivary testosterone and salivary cortisol both decreased from pre-daily exercise to post-daily exercise, with no change over the 21 days of intensified training. Figures 6A and B. Testosterone cortisol ratio increased from pre-daily exercise to post-daily exercise, but did not change over the 21 days. Figure 6C. Maximum exercise capacity. Maximum exercise capacity did not change over the course of the 21 days of intensified training in terms of peak oxygen consumption. 4.49 plus or minus 0.11 liters per minute pre 4.57 plus or minus 0.23 liters post. P is greater than 0.05 or peak workload 355 plus or minus 14 watts pre 365 plus or minus 17 watts post. Profile of mood states. There was no change in total mood disturbance, tension, or depression, anger, fatigue, or confusion over 21 days of intensified training. Vigor decreased from days 1 to 4 and remained lower throughout the 21-day training cycle. Figure 7. Individual response. The presence or absence of overtraining symptoms for each participant is indicated in Table 2. 4 individuals developed 2 or fewer symptoms, asymptomatic group, and 4 individuals developed over 2 symptoms, symptomatic group. The symptomatic group had a lower absolute VO2 max a trend for a lower max workload and lower performance during the 1 hour time trial than the asymptomatic group. There was no statistical difference between the groups for other select variables. See Table 3. Discussion. One of the novel aspects of the study is the method in which the data was collected. This investigation took place during a 3-week period of intensified training in the field, not in the laboratory setting. The use of a power meter incorporated into each participant's bicycle allowed us to quantify the work that was being completed over the entire 3,211 kilometer route during the 21-day period. Although the average work rate remained low, 47.2 plus or minus 1.1% of pre-training watts max, the daily mean time spent at an intensity greater than 70% of max watts was on average 71 minutes, of which 21 minutes was spent above 90% during each day of riding. Furthermore, participants completed a 1 hour time trial on 7 separate occasions. This design allowed us to aggressively stress the participants with both exercise volume, 418 plus or minus 142% increase in volume, and intensity while concurrently evaluating changes in their performance. A goal of this project was to induce a period of intensified training to put our participants in a state of overreaching, functional or non-functional. By definition, a decrement in performance must occur for the diagnosis of overtraining or overreaching to be made. The performance of the current subject did not significantly change, but did show a non-significant yet practical increase by an average of 4.3%. Therefore, despite the large increase in training volume, we were unable to create a training stimulus that had a negative impact on performance in these participants as a whole. Moreover, the only marker for overtraining used in this investigation that did show a significant change was a decrease in POMS category of vigor. However, without an observed measurable change in performance, singular markers of overtraining and or training may have limited diagnostic value. Although there are minimal statistical changes in the overtraining markers, it is possible that certain individuals may have developed signs of overreaching overtraining. To further evaluate the individual response, subjects were classified as symptomatic or asymptomatic based on the 4 markers of overtraining. Greater than 5% reduction in performance, resting heart rate increased by over 10%, increase of maximal exercise heart rate by more than a reported day-to-day variation of 8 beats per minute, and over 30% decrease in testosterone cortisol ratio. The individual with 2 or fewer of the symptoms asymptomatic group of overtraining had a higher absolute VO2 max, a trend toward a higher max workload, and produced more watts during the 1 hour time trial and the start of intensified training. Each of these differences in muscle mass dependent, and thus the amount of lean muscle mass appears to interact with the measured symptoms of overtraining. Furthermore, the asymptomatic participants increased their 1 hour time trial performance by 9.9%, whereas the symptomatic participants decreased performance by 1.3% during the 21-day period, pre versus post training between groups. Although it is unclear whether or not these markers analyzed here are good at detection of overtraining, they do seem to be indicative of training response. The intensified training period represented a 606% increase in training volume for the asymptomatic participants and only a 277% increase in training volume for the symptomatic participants. It seemed counterintuitive that no symptoms of overtraining were demonstrated in the individuals who had a greater increase in training volume, although symptoms of overtraining were demonstrated in the individuals who had a smaller increase in training volume. It is possible that the symptomatic participants were further along their individual overreaching or overtraining continuum, although no symptoms were present at the onset of the study, and that there may be a threshold for training volume that were exceeded during the study period. Additionally, the asymptomatic participants may have a more favorable genetic and physiological profile that helps them adapt to intensified training. These data further support the notion that individual athletes respond differently in terms of susceptibility to symptoms of overtraining. Interestingly, Symptoms that develop early in the training period did not always persist throughout the 3 weeks despite little time for recovery, Table 1. During these 3 weeks, only 2 days were used as recovery days, days 10 and 20. Overtraining is thought to result in a function of an imbalance between stress and stress tolerance, none at all. Have defined stress as the sum of training and the non-training stress factors. Furthermore, overtraining can occur when an athlete experiences high physiological and social stress, but relatively low physiological stress. During the current study, removing the participants from their normal living environment minimized many sources of extraneous psychological stress. The participants did not have to worry about school, jobs, scheduling, meal prep, etc., although the training stress was high. Other stresses were minimized by having high quality meals and by eliminating late nights, thereby providing an environment conducive to maximizing recovery. It is unclear that the control of other non-training stress may have impacted these results. In a 7-day period of intensified training, another investigation was able to see a decrease in performance when participants continued to live in their normal environment. Further investigation is warranted to determine the effectiveness of training camps for athletes when completed in their normal high social stress living environment versus an isolated training camp completed away from these stresses. Practical application. These data demonstrate that the markers of overtraining do not always parallel a decrease in performance and that these markers are unstable. The authors suggest that the markers presented here may simply indicate the presence of a training stress and not specifically overtraining. Others have also suggested that some of these markers of overtraining are characteristic of intense training and not overtraining. Anecdotally, many of these participants had their best competitive season after the conclusion of the study. Athletes, coaches, sports scientists, and clinicians must exercise caution when making the diagnosis of overtraining syndrome based on previously reported markers of overtraining. The criterion variables of performance and recovery must be incorporated, and as such, early detection may be limited. Furthermore, many athletes may be able to tolerate very high training volume and intensity without developing overtraining syndrome, particularly when they can limit their non-training stresses. Acknowledgement. The views and conclusions contained herein are those of the authors and should not be interpreted as necessarily representing the official policies and endorsements of either expressed implied of the Air Force Research Laboratory or the U.S. government sponsored by the Air Force Research Laboratory under the agreement of FAA 5650-06-2-6740. The results of the present study do not constitute endorsement of any product by the authors of the National Strength Conditioning Association.